Thank you again so much for being here, everybody. I just want to introduce myself. I am Ashley Lee. I'm based here in Las Vegas. I am the Amargosa Conservancy president. I've been here in Las Vegas for about 10 years and been on the board for 3 years. And just really happy for us to provide these type of educational opportunities to let people know about what's going on in the basin, because it is such a remote and rural location that we want to be able to convey enough information so you guys can support different campaigns that are going on and understand why this area is important. So tonight we have the amazing Andy Zdon coming in. He's been doing work in the basin for over 30 years. And he is doing a lot of work monitoring. He's found out a lot of different complexities with how water flows, and it really helps us as an organization make decisions and help share to legislative and decision makers about what's going on in the basin. So I'm going to go on mute. Thank you, everybody, for coming in. Introduce yourself in the chat, and I will post a few links throughout the chat that are linking to our newsletter. So if you're not on our newsletter, it's a monthly e-blast, and twice a year we have a physically mailed in paper newsletter that's really beautiful, and it's tabletop and you can keep it and just reference it. It's really beautiful. So if you're not signed up for either of those, I will put the link in. It's just on our website, amargosaconservancy.org. And then also, which is new, we have some merchandise available. So if you want to support the AC further, you can support us with some merchandise as well. So thank you again for being here, and I'm going to let Andy take over. Thanks, Andy, for being here.
Oh, thank you. Hello, everybody. Really, it's wonderful to be able to present what I'm going to be presenting to you this evening. Though I have some tech issues where you can either see me or see the two coyotes, and I think you'd prefer to see the two coyotes. So my one camera is going to stay closed here. But so my name's Andy Zdon. I'm a hydrogeologist with Rue Associates in Oakland, California. Although I'm based in Oakland, I'm sitting here at my home in cool California in the Sierra Nevada foothills near Auburn. And yes, I've been doing work out in the Amargosa for a long time. This all really started in earnest back in 2009, coinciding with the designation of the Amargosa River as a wild and scenic river. And in planning for a future management plan for the river, it was recognized that there was really an absence of data on which to base a real meaningful management plan. So the Amargosa Conservancy got a grant, substantial grant, to do sort of a baseline spring investigation. And we went out and went to all the different springs and sampled them for geochemistry and just identifying where they were and all their physical characteristics. And I was sitting in my office one day and the lab results came back. The general chemistry came back and the results seemed to be all wrong for what we expected based on the just general understanding, which was based on really very little data, but general understanding of how groundwater is moving. So I got on the horn with the lab and said, there must be some problem. I think you guys messed up some samples. Can you reanalyze these? They got back to me and they reanalyzed them and it came back the same. And so I thought, uh-oh, I wonder if some of these samples got mislabeled. So we went out, sent my person that was doing a lot of the field work out to resample several of the locations that seemed particularly anomalous. And those results came back, again, the same. And at that point, it was pretty clear that we had a lot to learn about how groundwater was moving through the system. And essentially that moment has sort of changed my life and the trajectory of the work I do, where this has really become a focus, not only in the Amargosa, but the types of things we've been learning here have actually been translating into work throughout the California desert and actually beyond into Nevada and Utah. So anyway, it's been a real pleasure and a real privilege to be able to work on this. So this evening, this was advertised as a hydrology of the Amargosa, and I'm going to do something a little different. We're going to go through some hydrogeology in a few slides. I'm going to introduce a concept or two that will follow through the program. And then I'm going to introduce you to the monitoring network that we typically use for our periodic monitoring and kind of work we have done. And then I'm going to give you a little summary of some of the things we've found out, which are particularly interesting, and a synopsis of what current conditions are and current trends in groundwater levels and in springs. And then I'm going to take you on a little tour. I periodically give tours, spring tours for the Death Valley Institute. And I'm going to give you sort of that tour in this form, although I'm going to be able to provide you sort of historical change. So you're going to see photos for individual slides where you can see the changes over 100 years. Some of them you'll really only need to see them for 2 years to see substantial change. But I think it'll be very interesting. And then going to wrap that all up with kind of talking about how all this information can be used for assessing projects and managing resources and using modeling tools to evaluate change in the system. So as I mentioned, when we started this effort out, there was very little information on springs in the Amargosa, and springs are really critical. Actually, I consider the Amargosa River essentially the granddaddy spring of the basin, because it is a groundwater fed spring, and a spring is basically a natural groundwater discharge point. But there are a whole slew of feeder springs that along the wild and scenic reach of the river and beyond. And so as we went into this, we were looking for data, and in how far back did we really need to go to really find a consistent data set? Well, it was really the last really systematic look at springs throughout the Amargosa, and in fact, in the California desert in general. It goes back to a report that was prepared by a geologist named David Thompson back in the 1920s. He actually did 2 papers, one in the early 20s and one in the late 20s. And they're kind of collector's items now, but they are really detailed, essentially road trips through the California desert describing water resources. And that, thankfully, that record is there, because that really provides what in my mind is the real baseline to compare what the current conditions are to. And when you look back over that essentially nearly 100-year period now, some of the changes are really striking. So before we go through and talk about what's going on, I should kind of get you up to speed with the geography of the area here. So this blue line, this bright blue line, is what is designated as the Amargosa Wild and Scenic River. We have Shoshone here and Tecopa down here. To the east, over a mountain range or two, lies Las Vegas. To the west, over a couple of mountain ridges, lies Death Valley. To the north, this is the Nevada-California state line, and Death Valley Junction would be right just at the top of the figure. And Highway 127 winds down here. Here's Salt Creek and continues on into Silurian Valley and down to Baker. We can kind of see where we are relative to California and Nevada here. There's this orange dotted line, which there are differing opinions on how far the limestone or carbonate rock aquifer extends from Nevada into California. This is the line from the most recent conceptual model report prepared by the USGS. And then we have a series of springs here. Those are in green, like Chapo Spring, Borax Spring, the borehole, which is not really a spring. We'll talk a little bit about that. Tacoma Hot Springs and others. Oh, by the way, this was a typo that was in the original figure. These are not Amargosa Conservancy spring areas. They are Amargosa Canyon spring areas. And Willow Creek by China Ranch. And then I've added 3 other springs here. 12 Mile Spring, which is a very important spring for our studies and historically. Tule Spring, which is down in a little sub-basin of the Amargosa here called California Valley. And Schofield Spring, which is actually, I was going to talk a little bit more about it. I kind of left it out just for time frame purposes, but what's really neat about it was a spring that wasn't showing up on any of the maps when we did a big, large spring survey in 2015 and 16 across the entire Mojave Desert. And I was in the car with Patrick Donnelly, and he was looking up to the Nopah Range, and there was this little spot of green up against the range. I said, "Oh, that could that be a spring?" And it was, despite the fact that it was like 100 degrees, we hiked up the alluvial fan, and sure enough, it was a spring that nobody we knew, BLM was not aware of it. Nobody we knew in Tacoma was aware of it, but it's a spring. We ended up naming it Schofield Spring. And we saw literally no sign of human presence there. It was one of the few springs that we go to where you don't see any sign of human presence, just the footprints of wildlife, which was very cool. So our story actually begins up in central Nevada. So a lot of the water, a large portion of the water that makes its way down to the Amargosa Wild and Scenic River starts its journey up in central Nevada. And as you can see, there's this flow path that comes down out of Lincoln County. You see all these areas that have the diagonal lines in them. Those are all carbonate rock or limestone rocks that act as really good aquifers throughout the central and eastern Great Basin. And a large portion of that water, you can see water moves down from Lincoln County, and then part of it goes off towards the Muddy River and out to the Colorado River, and then a portion of it heads down towards Ash Meadows and the Amargosa Desert, and then beyond down into Shoshone, Tacoma area. Once you get into California, and you dial in a little bit, the flow paths become a little bit more complex. So we have this big blue arrow, which is a flow path of water that moves from north to south from Nevada past Death Valley Junction, and essentially is making its way as underflow along the Amargosa River, and also very likely along faults that run parallel to the Amargosa River here, and may extend east of Eagle Mountain, which is this mass of rock right here, up into the Ash Meadows area. We'll talk a little bit more about that. There's another flow path that extends from alluvium through carbonate rocks and back into the valley fill of Chicago Valley here. This is Pahrump Valley off to the right. Another flow path into the basin comes through California Valley, again from Pahrump Valley through California Valley and towards Willow Creek. And then there are these other little sub flow paths that come through various areas where water finds its path of least resistance, either through limestone or alluvium down towards Shoshone and Tecopa, and then everything's moving down through the Amargosa River Canyon and off to Death Valley. One of the reasons that you have surface flow in the Amargosa River Canyon is because that groundwater is meeting the rocks of these hills where you find Willow Creek and the canyon itself, and has nowhere to go because the bedrock is much less permeable than the alluvium. So the water is just forced to the surface and you have that flow. And then once it gets out of the hills, back down into the valley fill again down here, it starts soaking into the ground, and depending on the season, can make it all the way to Death Valley as surface water or not. It's really important here to look at where these arrows are coming from. The large groundwater use in this basin is not anywhere within the California portion of the basin, but is in Nevada. So the large pumping centers historically have been in Pahrump Valley and in the Amargosa Desert north of Death Valley Junction. When I talk about the pumping here, it's been very substantial. And this is a picture I took from the top of the Tecopa Hills, looking at the Amargosa River, and this is where you kind of see where the Amargosa Canyon is off the picture to the left. But again, as the playa is narrowing and as that valley fill is narrowing, the water has nowhere to go, so you can see it seeping up through the surface. And this is really where the perennial flow really begins. So when I talk about pumping, and one of the things I'm going to be talking about is lowered water levels or a cone of depression. And what is that? Well, let's assume here for a moment that this well isn't here, and this water table just is sitting here. Water's moving from left to right in this figure. You have various little recharge sources here, and you put a well in and you start pumping that well. Well, what happens is initially the water level in the well drops as a response to the pumping. And then it results in this conical feature called a cone of depression. And that's the depressed groundwater levels. And that allows water to flow towards the well. Eventually, at some point, assuming that the well, there's enough water to meet the needs of the well, this system will stabilize. But for it to stabilize, that means that other aspects of either recharge or groundwater leaving the system or plants using the system, discharges, has to decrease. So there's a thing called the groundwater equation, which is inflow minus outflow equals change in storage. Storage refers to the amount of water that's just sitting here in the aquifer system. The inflows are like underflow, or if a river is recharging the aquifer. Outflows can be evapotranspiration from evaporation from surface water, or transpiration from plants, or pumping, or underflow out of the basin. But regardless, whatever you're pumping ultimately will be offset by changes in those inflow or outflow components to adjust, make the system stabilize. Now, in the desert, where you don't have much recharge, and when it comes to this precipitation, there's sort of like nothing to see here. It leads to one of the more challenging aspects of groundwater management, and that is, if you turn this well off, what happens is the water level will start rising in the well. It'll start recovering, as you kind of would expect. But absent these different recharge sources, what can happen is, in order for that to happen, water has to be pulled in from further and further out. And so when you turn off the well, although right around the well field, you'll see recovery, the effects of that pumping can continue at distance, like large distance away. And in fact, say you're pumping a well field for 50 years at a very high pumping rate someplace, and you turn off the wells, well, the water levels in the well field may recover in 30 or 40 years, but 20 miles away, water levels may continue to drop for, another 50 years or 100 years or more and beyond. So that is one of the challenging aspects of managing groundwater, is because that response in distance, there's nothing you can do about that. So once you've turned off the well, for instance, if say there was a spring where these trees are and you started to see this cone of depression develop under it, and the water level started dropping and spring flow started decreasing. And so as seeing the effect at the spring, you turned off the well. Well, it may be too late for that spring at that point, because although it's recovering here, it may be continuing, the water levels may continue to drop here for another 50 or 100 years, and the spring may be lost. So the tricky part is catching these changes or excessive changes before they affect resources. So, and then when I talked about pumping, pumping in, like, for instance, in Pahrump Valley has been substantial. And just to give you an idea here, this was from the 2020 State of the Basin report. And I suspect there was probably more pumping prior to the late 50s here, but it just wasn't, there weren't records kept. But you can see pumping reached almost 50,000 acre feet back in the 1960s, again in the 70s, and even now has sort of maintained somewhere between 20 and 30,000 acre feet for the long term. And keep in mind that these numbers don't include pumping from domestic wells in the basin. This was actually largely driven by agriculture back in the day. For comparison, the actual recharge to the basin is somewhere between probably 15 and 20,000. I think the number that's used now is 20. The number that was formerly used was 14. So, even if it's 20, in general, pumping has been exceeding the recharge rate to the basin for quite some time. So in order to sort of understand the hydraulics of the system and to understand where water is flowing and what water level trends are and how that compares to what we're seeing in springs, we've had two essentially monitoring well installation events. The first one, which are the 4 blue stars, and I apologize for the fuzziness of this figure, were monitoring wells that were installed back around 2010. They were funded by the Nature Conservancy, and they were our first look. And that this particular star was the first well we installed. That one was a rather startling well. So that's right next to the Amargosa River. And as you hear that, it's always talked about that, yes, the Amargosa River is dry, but that water's moving along right beneath the surface. Well, when I would drive past that all the time, whether even in the area to climb peaks or just explore, it always bugged me because the plants weren't right for that channel. You would have expected, if water was beneath the surface, you'd expect the plants, the types of plants, to reflect that, and they just don't. So that was a point of curiosity, and that was the first place I wanted to put a well in when we got funding. And so we drilled right next to the Amargosa riverbed. We drilled through, I think it was about 50 or 60 feet of river gravels. They were dry. We drilled through about another 90 to 100 feet of Tacoma lake bed deposits, and they were dry. And when we punched through those lake bed deposits, we hit a saturated gravel. The water level rose about 50 feet up the casing, and it was 100-degree water. And it turns out that geochemically, and we've gone into some really esoteric isotopic methods to look at those waters. Those waters were a dead-on match for Shoshone spray. And that was like the first well. And it was like, okay, now we've got surprises. And essentially, as we've gone through this, even through the second round of monitoring wells, which were paid for through a grant that the Amargosa Conservancy got with the California Department of Water Resources, as we put in monitoring wells, they've each had their own surprises and have been really, really valuable. So they vary in depth between 30 to 200 feet. We have all of them outfitted with automatic groundwater level measuring devices, and they take a water level measurement every day at 4 p.m. and 4 a.m., which results in a lot of data over 10 years. But I wanted to see if we could see effects from seismic activity. And you need to have it's kind of a balancing act to do that. And we had to wait almost 10 years to see that, but the Ridgecrest quake, the July 4th Ridgecrest quake, that's a mouthful, that happened a few years ago, resulted in responses of varying amounts in all of our monitoring wells. We also, this is what putting in a monitoring well looks like. We actually use a drilling method called sonic, which provides really great, fine, detailed samples. And so you get some really great geologic detail on the well logs. And it's also pretty economic method to use. So anyway, that's what a well installation rig looks like. And then we also have a network of springs that we periodically monitor. And now after 15 years, we're getting records long enough. We try to monitor 3 times a year if we can, if we have the funding to do so. And we're finally getting records that are long enough where you can really statistically look at trends and see what's happening in various different springs. But we'll go through a list of these springs. We also do some periodic monitoring of springs that are much more distant from the Shoshone-Tacoma area. Kingston Spring is a very, very cool spring that is at the southwest base of the Kingston Range. I wouldn't even begin to be able to describe how you would get to there. I guess you would say you would turn off a really rough dirt road from Highway 127 south of Salt Creek and just drive forever across the desert. And eventually you come to this incredible oasis that's like a grassy, wet meadow. Sheep Creek is up in the Avawatz Mountains, and I have to admit it's one of my 3 favorite springs to go visit. It's basically a little perennial creek that's high up in the mountains. And then there's these other springs that in various areas that we go to. One of the things that we see is that when we've done the geochemistry of these springs, from east to west, there is a gradation in the influence of either waters from Pahrump Valley to the east or from Amargosa Desert to the north. So essentially 12 Mile Spring, which is the Chicago Valley, which is just over the mountains from Pahrump Valley, is essentially identical with waters that you see in wells in Pahrump Valley itself. Meanwhile, if you go all the way over to the other side of the valley at Shoshone Spring, the waters are almost entirely a perfect match with waters you see up in the Amargosa Desert, Ash Meadows area. And in between is sort of a mixing line. So you have a sort of a gradational difference in waters that as you go from east to west. Also, early on, we did some isotopic work to try to evaluate whether the heat of the spring water in Tecopa Hot Springs was either from a shallow magmatic source or from or just from deep circulation along faults. We were using helium isotopes for that, and actually what we found, it was just deep circulation. But given the temperatures of the waters, that is very deep circulation, thousands of feet deep that water is coming up along fractures from. And so what this all points to is that, in the past, people would really single-mindedly focus on Front Valley as looking at things that could affect the system. But now we know that both to the north and the east, Amargosa Desert and Front Valley can influence conditions along the Wild Scenic River. So one of the things that we do some sort of age dating, or look at the residence time, essentially how long has the water been underground? And generally, and this is really common throughout the Mojave Desert, maybe not to these numbers because these waters have had a much longer flow path, but the waters tend to be thousands of years old. And here we have, for instance, Tecopa Hot Springs in the borehole, radiocarbon age of 28,000 years. Now, when you try to say, well, what did that rainfall look like back in the day? Well, it was a completely different world. 20,000 years ago, for instance, there was no San Francisco Bay, and the Farallon Islands were not islands because we were right in a really strong period of the Pleistocene, and the sea level was 400 feet lower than it is now. Meanwhile, there was tons of water out in these desert valleys at that time. So it was when you try to envision what it might have looked like back then, it's a very different picture. Thinking about mastodons and saber-toothed tigers wandering around, it was a much more dangerous place then. One of the things that we kind of look at is we also look at tritium. So tritium gives you an idea, and there you can really fine-tune ages with various methods using tritium. We're kind of looking at, is there a new component of water, or is it all old? Or is it all new? And so basically, we're just wondering if tritium's present or it isn't. And for instance, in the case of the Sawgrass Spring, which is one of the springs that's in the Amargosa Canyon, and I'll be showing you some slides of that later here, we picked up a detection of tritium. Now, that was a particularly clear, nice sample, and so you see that number is actually lower than some of these others that have higher numbers and show as non-detect below a certain detection limit. So it doesn't mean that tritium isn't in those other ones, but they just could not get a detection limit down to those kinds of levels. But if you have water that's 18,000 years old and you can observe tritium, it's telling you that there's a mixture of older waters and newer waters mixing together, and that the older component is probably something older than this 18,000 years. But without doing a lot more work, you don't know what that ratio of the older to newer water is. You just know that there's mixing going on there. For the purposes of really, though, understanding what conditions are and what's happening to water levels in springs, though, I've kind of summarized here what is going on in our monitoring wells since we've installed them. So ARHS1, which is that well that I talked about, and it's about right here, north of Shoshone. If you can see my little arrow there, it's about 4.5 miles north of Shoshone. That was actually fairly stable, and then there was a little period where the water levels dropped a bit, and then it's kind of stabilized again. But over the 11 years that we've been monitoring that well, the water levels dropped about 1.25 feet. And that means about 1/10 of a foot per year as a decline. Now, that number may not sound like a lot, but I'm going to be showing you what a couple feet of drawdown and some of these means for some of these springs a little bit later. We have a monitoring well at Willow Creek that we originally, which is on the China Ranch property, that we originally put in, but at this point, there's a reservoir at the upper part of the property at China Ranch, and whatever the water level is in that reservoir affects our monitoring well. So that has less value, although what we can see looking at it long term, despite all its jumping up and down, is it's pretty stable. 12 Mile Spring, which is, our well at 12 Mile Spring, which is over in Chicago Valley, which is just over the mountains from Front Valley, has dropped 1.6 feet. It's dropping about 1/10 of a foot per year. I can tell you that is just a point in time, and I'll actually, let me go through the table and I'm going to mention something here about that. Married Man's Camp, which is on a Amargosa Conservancy property east of Tacopa at the headwaters of Willow Creek, is stable. Actually, did I do something here? No, that's what it is. So it has been dropping a little bit of late. That's been dropping too. Dumont, we have a monitoring well at the foot of the Amargosa River Canyon on the Dumont Road that is very variable. Again, it's controlled by whether there's flood flows on the Amargosa or not. So you can, if there's water flowing in the river, the water levels will be around 70, 80 feet. And if there's no water in the channel, the well's dry. California well, ARHS 06, we were getting a downward trend on water levels. And then between the Ridgecrest quake or roots from nearby aethel trees, something fouled that casing. Either the casing collapsed as a result of the earthquake, which could have happened, and because we did see a substantial change in the well adjacent to it, this Davis well, or it's just clogged, but that's going to need to be replaced. ARHS 7 was going to be a monitoring well between Shoshone and Tacopa along the river. That was not installed because at the time we were installing the wells, there were marshy conditions, and we felt that we would actually cause more damage than the data or the effort would be worth. So we ended up not installing that well. ARHS 8, which is up here just south of Eagle Mountain. Again, you would expect that trend to be similar to the first well, ARHS 1, but keep in mind that it's a much different period of record. And so, this is what we're sort of seeing over the last few years. Stewart Valley is this valley just near the state line and at the north end of Pahrump Valley. And that has been very consistently dropping at 0.3 to 0.4 feet per year, which adds up over time. And then finally, our well, ARHS 10, which is right next to a spring called Tule Spring, has been dropping almost 0.3 feet per year since 2018. That one was largely affected by the Ridgecrest quake. We had this downward trend that is along these lines. And then when the quake happened, there was this like bump in water levels. And after the quake, the water levels started recovering on that at the same, essentially the same slope as they had been declining pre-quake. Interestingly enough, Tule Spring started actually rising as a result too. About 2 months later, now if the Ridgecrest quake was along essentially the Garlock Fault, and if you extend the Garlock Fault eastward past the Avawatz into the basin, you'll actually end up along the north slope of the Kingston Range in the same valley as where these wells are. About 2 months later, there was a little microquake, and that we saw that response in the well as well, and in the spring. And the water levels then after that quake started dropping like they had before, and Tule Spring started dropping as it was doing before as well. So generally, there's a bit of a groundwater decline across the basin, less so on the west, but it's pretty significant on the in the wells most adjacent to Pahrump Valley. So looking at these springs over time can be really interesting, and it's particularly interesting to go back into the historical literature and find historic photos of these springs and to see how change has happened. This is a photo of the head of Shoshone Spring in around 1928. This is actually the pupfish pool down below currently. And actually, if you go out to this area right now, it looks very similar to what it did back in the 1920s, except for there's a spring box here because that's the source of water for the town. But again, this is springs on the west side, like Shoshone Spring is, haven't been affected. We haven't seen changes to those springs. Similarly, at Borax Spring, which is actually not a spring, but is our flowing artesian casing that was installed, and we can't seem to find records for that installation, but it flows at about 8 to 10 gallons a minute and has been very consistent both in water quality and in flow rate for as long as we've been monitoring it, since 2010. Again, this is down along Highway 127 south of Shoshone. If you see this big pond along the highway, in fact, that's the highway right there. You see this pond, that's where Borax Spring is. This is what this area looked like back in the day. So there was one of the original borax works, of the Amargosa Borax Works, was situated here in the 1880s. When this photo was taken, it had long been shut down, but as you can see, there was no spring there at that time. And I mean, basically, these buildings are where this meadow is now. So this was a case where this wetland, which doesn't see a lot of use from wildlife. The water is very highly saline. It's really a brine, very high in boron, just really kind of probably the nastiest water, natural water in the that we've come across in the basin. But this little oasis here was formed by this one casing, which may have something to do with minerals exploration, similar to what the borehole was. This may have been like a mini borehole. Moving to the east on the other side of the basin, where we've seen water levels declining more. This is 12 Mile Spring up in Chicago Valley. And back in the early 1900s, there were reports of, because the main road through Chicago Valley used to actually go to this spring. And they would fill barrels of water here for the livestock as the wagons were going from mining camp to mining camp. And even as late as the 50s and I think into the 60s, maybe, there were some of the locals in the Shoshone and Tacoma area would talk about going out there, and the water used to flow around the backside of the spring out to the front. You can actually see where the old channel was, and declining water levels over time has caused this thing to slowly dry up. And although we've been monitoring since 2010 this spring, I wanted to just compare, just in a short period of time, what we've seen. Here's April 2019. You can see this hole here is filled with water. There's a little bit of spike brush growing here, and the water is actually extending over into just out of this hole and around the corner here. Now, granted, it's nowhere near what it used to be, where it was flowing completely around this whole system, but just in the period of 2 years, you can see this is just wet soil, and now there's essentially either animals or people have dug a hole that's about 1.5 feet deep, and there's just a little tiny puddle at the bottom of that hole. That change is the change you can see with 1 foot or even maybe a little less of drawdown. On some of these alluvial springs, it doesn't take much to cause really a big effect. Now, we used to see occasionally maybe signs of bighorn sheep at this spring. I haven't seen it lately. Most recently, I think this was actually the last time, if I'm not mistaken, that we actually had enough water in here where we could actually measure water quality, and essentially is just moist soil now. There is no surface water present. It still supports the plants because the groundwater level is still shallow, but there isn't the surface water for wildlife anymore. The borehole. So the borehole is the warm springs you see as you head north from Tacoma Hot Springs, and you see all the bathers off in the mud hills out there. The borehole, we used to call it borehole spring. It is not a spring, so I just call it the borehole now. The borehole formed in 1967 when the Stouffer Chemical Company drilled an exploratory hole looking for minerals, and encountered at around 350 feet an artesian flow that they could not control of hot water. It started eroding out the hole. The drill rig actually tilted into the hole a bit. Lots of attempts to clog the hole, to control the flow, failed. That included putting 10,000 cubic yards of gravel down the hole to try to help stem the flow. And these are the remnants of that gravel pile from back in the day. And none of that worked. While that was happening and they're trying to control the flow, in relatively short order, a Mr. Tom, T-H-O-M, who had a warm spring on the south end of the Tacoma Hills, noticed that his spring was dropping, spring flow was dropping, and the water levels in his well were dropping. And he came over and was rather upset, to say the least. And that was one of the first signs that essentially what the borehole did was partially depressurize the Tacoma Hot Springs spring field. So if you go around the backside of the Tacoma Hills, there's a spring line along the fault along the base of the hills there. And you can tell that there was once a lot more water than there is now. In fact, it's virtually dry. In fact, there's an old bathhouse that used to have water and no longer has water. So this not being a spring, but being a well, it behaves more like a well behaves than a spring would do, where it would just be kind of flowing consistently. Over time, the flow has dropped. And if the flow has dropped from when they first encountered the flow, and it has flattened out. And if you look at short periods of time, it looks relatively stable, but over the long term, the water levels are slowly declining, and I don't think it's fully stabilized yet. And so, we're still seeing the effects of that in neighboring springs. Going a little south, here's Tacoma Hot Springs. And so it's not only pumping that changes springs, but just are the things we do for development and just changing land uses. So here's Tacoma Hot Springs back circa 1948. You can see that the water has has these little incised channels in the lake bed deposits here that make their way out to the marsh. Now, this hill right here is this hill right here, which is a more recent photo taken from the Inyo County website for the park, the Tacopa Hot Springs Park. And you can see that there's been lots of development here. There's been lots of fill brought in. The outflow from the hot springs has been diverted and actually fills the pond, which helps with waste treatment. But I think the bigger story here is, and some of you may are familiar with the Amargosa vole. It's a endangered, very critically endangered mammal that lives in the bulrush marshes. And if you look in the upper photo, here's that hill. You can see all this water was making its way down to a very large marsh down here. And you can see that that was all wet. And you can see here that that has disappeared. And that was a big chunk of habitat that's gone. So that's where it wasn't so much pumping as much as it was surface use and regrading and things has changed the system dramatically. What happened, how these were filled, do these channels still exist in the subsurface, and is there preferential flow along them? Hard to say, and that would be maybe something you could look at with geophysics, but anyway, substantial change. This is an interesting location in the Amargosa Canyon. This is what we call Sawgrass Spring. So back in the day, the old Tonopah and Tidewater Railroad ran through the canyon. And this is a large cut here. This block of rock used to be connected to that block of rock. And it's a big cut, and the railroad grade it goes right between them. This is actually that cut. This is Red Cut. It's named for the red rocks here. And you can see back in the day, they would actually run the train through here. They would run these pipes and actually drill into these seeps that they had encountered when they cut this. And they would collect water for the tanks for the trains. And when they cut this thing, it caused the moist conditions caused a slope failure, which I believe is this scarp-like feature here. And this is essentially slide material and probably provided the substrate to really allow the vegetation to really take off in here. And this is one of the springs that we do monitor. That's the one that was 18,000 years old, but had tritium as well. In fact, here's somebody up here trying to take measurements up on the debris and in the thick vegetation. But again, now this is a case here. This is kind of striking because you can see how little vegetation there is and how the vegetation has moved in now that it's had a place to go and a water source to follow. Resting Spring. So Resting Spring is one of the most famous springs in the basin. It was probably the most critical spring along the old Spanish Trail in the area. It was a large spring. Back in Thompson's day, he estimated it's flowing, I think he was calling it 240 gallons a minute. And you can see back in the early part of the 20th century, they used it to grow hay. Here's a photo from the Hafin's book on the old Spanish Trail from 1954. I'm not sure when the photo was actually taken. But one of the things that you see now, and I'd love to get back to this location and take a photo. From the highway, I suspect that mesquite is in here. A lot of these arroyos have been filled in with mesquite and have kind of some ideas, speculative ideas on why that is. But beyond the hydrologic changes that have happened, back in 2010, When we started this, we actually got permission to get on the ranch. It's privately owned, and it's in the hands of a trust, and it's quite the gauntlet to try to get permission to go on the ranch. But we measured this flow at around 180 gallons a minute at that time, which would have been lower than what was previously measured. But at the time, we thought, well, it could be just the measurement method. So we weren't sure what we were going to encounter when we get out there. Essentially, right now, all of the flow from Resting Spring is captured in a big spring box system, and this is the discharge point, and it's distributed across the property. But later on, there were other springs that kind of pointed to, well, maybe that number is pretty real. And what really drove that home is Chapo Spring. So if you're out by the borehole and you look across to the Resting Spring range and you squint really hard and kind of close your eyes and the lighting's right, and preferably if you have a pair of binoculars, you can see these palm trees sticking up against the mountains. And that's the site of Chapo Spring. So that was kind of a puzzler because clearly there was something substantial there. And I was not finding any old records on Chapo, and I discovered well into this after doing some detective work and some sleuthing and looking at Thompson's work that Chapo was a later name, and it was formerly called Yeoman Spring after a Tecopa miner who had the property for a little while. And back in Thompson's day, he reported flows at 10 miners inches. Now, miners inches. So depending on the state you're in, that number can be different. So in Nevada, a miner's inch is 11.2 gallons per minute. In California, it's 9 gallons per minute. I mean, that's 9 in Nevada and 11.2 in California. Regardless, what's important is back in the day, it was probably flowing around 100 gallons a minute. The California Department of Water Resources had a statewide report on water conditions across the state, and it listed this spring, and they listed it as a warm spring, along with Shoshone, Resting, Willow Creek, and Tecopa Hot Springs as the principal springs in the area. So even then, it was pretty substantial. But think of that year, 1964. That was also the peak year of that Pahrump pumping that we saw on that graph. And if you go out to Chapo Spring now, what you'll see at the spring vent is this essentially little puddle. Actually, the last time I was out there, this was actually choked with like cattails and things and palm fronds, and you couldn't even see the water. And a little bit down the creek is flowing maybe 5 gallons a minute. And what that's telling you is that, well, wow, that is a huge change. Now, back before we even started this thing, we were at a meeting in Las Vegas, and the USGS was there, and we were there, and other agencies were there, and we were all talking about, because there's really, prior to this effort, there was no recorded, nobody noticed the changes to these springs. And one of the questions was, well, if you had all these impacts happening to springs in Pahrump Valley, why didn't we see that over in the Amargosa, over in Shoshone and Tecopa? And that was really kind of a puzzler. While diving into this, we discovered that those impacts did happen. It's just that it happened slowly. And one of the things about working in the desert is you got to wrap your head around the idea that, and get folks understanding that change, especially in large groundwater basins, you're looking at potentially irreversible change, but you're going to only see it on a sort of a generational time frame. So if you were out there, so we lost 90 gallons a minute over about 100 years. So, if you were out there in 1955 and it was flowing at 70 gallons a minute, and you went out in 1956 and it was flowing at 69 gallons a minute, you wouldn't be able to tell the difference, especially since it was engaged. And you probably wouldn't have noticed the difference between 60 and 50. And then you leave and there's no record of it. And so change happens slowly over 90 years, and it's not essentially not noticed until you can have a old record to compare it to. And so that's why I was saying Thompson is really what I use for what baseline conditions are. But this really showed that this part of the basin really got hit. It was a substantial spring for DWR back in the 60s. So probably most of that change really did happen since the 60s. So again, it happens. It still means it's slow, but a very big change in the system. This is Tule Spring. This is the one next to that California well that was really hit by the spring. And you can see this was actually an old watering hole. It probably never was really ever anything much, but it was essentially a place where water could be got. It was along an alternate route along the old Spanish Trail. If you bypassed Emigrant Pass, you would go down past this spring. So when we first monitored in 2010, this is what it looked like. This is actually a kind of a deep hole over here. And then the water had filled that up and was kind of running out of it, out into the flats here. By 2010, the water level had dropped about a foot or so. And essentially this was a little mud puddle down deep in the roots of this big cottonwood tree here. And then by January of 2023, essentially the spring was dry. And actually we had to dig out the cottonwood leaves to actually find just a little bit of moist soil. But that water level decline coincides with the magnitude of the water level decline we're seeing in the well. And again, that's really reflective of only less than 2 feet of decline in this time period. 2 feet makes a difference on these alluvial springs. And then finally, I'm just going to wrap up with the spring looks at Tom Spring. Now, Tom, as you remember, was the spring that was first hit by the borehole effects. Back when we first started visiting Tom Spring with the Amargosa Conservancy back in 2006, 2007, if you drove up to this aphel tree, and the spring vent is right up just below this tree here, you would drive up and you would actually turn off your car. And if you listened out the window, you could actually hear the trickling spring brook issuing from the rock. And the water here, as you can see in 2010, was flowing down through all this vegetation and flowing down. And actually, at times, it was actually even more than this. In fact, in this picture, this is a much later October 2021. You can see there's this kind of dugout area right here. Back early on, I think probably as late as maybe 2015, 16, there was enough water where that would be completely filled with water, and there was a large crawdad and mosquito fish living in that. That hasn't had water for quite some time. And back by the time October 2019 came along, there was just a little bit of standing water that was barely enough to get our probe to collect a measurement. And most recently, the last couple of monitoring events, there's just been, again, moist soil, but no actual flowing water. And the other thing is we're starting to see a little bit of a change in the vegetation qualitatively. As much as I'm not a botanist, but looking at this, it appears that a lot of this bulrush is receding and the arrowweed is starting to move into that. So, I mean, it is seeing a change to the reduced flow, and that may come from partially from the borehole, and it may come from partially from reduced flow from that Chicago Valley to Copa flow path. So when we collect all this data, when a project comes up, one of the things that is typically done is all that data is meshed together and used to develop a groundwater model. And the groundwater model one of the first things to when you're developing a groundwater model is you're going to design it around a particular question, because no model answers all questions. But you also have to really keep in mind how you design it for the questions you're going to answer. Now, this was a model of Pahrump Valley that Desert Research Institute put together, and for their purposes, it did a fine job, and it was actually this is a very standard method of designing a model. They used the watershed boundary essentially of Pahrump Valley here to look at this, and they were allowing for underflow through the basin along this line into the Shoshone-Tacoma area, but the type of boundary they used actually specifies groundwater elevations at some distance from that. And so that kind of stabilizes what happens. So you're only going to be in this model predicting what happens up to the actual model boundary, which is what you see here. Now, based on the data that they had, this is the map that is showing what field measured conditions were. And this is actually what the model is predicting. But really looking at this, so that this kind of ends right here, but that's partially because there's no data here, or they weren't aware of there was data here. But Chicago Valley, we have a well here. Down California Valley, we have wells here. We have springs down here, Chapel Spring, whatnot. And what we know by having this data is that these water level declines have really extended like way down here and off the map and way something like that. And so that's where having these new monitoring wells, which monitoring wells were non-existent prior to this effort in the Shoshone-Tacoma area, is just really critically important in understanding what's going on. The other thing is, again, what questions are you trying to answer with the model? For instance, if you're concerned about springs, especially springs and alluvium, we're seeing what can happen with just 2 feet of water level decline at one of these alluvial springs. And you can see that really, that's just like one little tick mark here of water level change. And so essentially, and really probably there's more error in the actual measurements than what you can see there. So what that would be telling me is that, okay, we've got changes happening here that the model may not be refined enough to be able to pick up. And that's just telling you that something's happening here, and you're going to need, in the absence of really more fine-tuned data and more data, you're just going to have to manage conservatively, recognizing that there's a lot of unknowns, and in water, as in anything, uncertainty equals risk. So with all that, that's sort of my talk. With all that, I do want to just acknowledge all of the groups that have contributed to this Amargosa work. Amargosa Conservancy has sort of ramrodded this whole effort going back many years, provide the initial funding for the work through a grant, and then later got the large California Department of Water Resources grant, which allowed us to put in the last 5 monitoring wells and conduct 3 years of spring and well monitoring. The Nature Conservancy, which paid for the first 4 wells and paid for a number of monitoring events. I represent Inyo County on things related to Yucca Mountain. And as such, Inyo County has also chipped into some of the monitoring out here, and also looking at evaluating for instance, the new Death Valley 3 groundwater model, which we put through its paces and we have up and running. California Department of Fish and Wildlife has provided some funding that supported this, sort of related to the vole. And although there are different purposes for some of the work that we've done out there, they all contribute to sort of the central telling the big picture of the Amargosa Basin.